Now, the most powerful intelligence on this planet is talking to you. But here's the problem. That intelligence doesn't have a brain. ChatGPT doesn't understand your question. It doesn't think. It doesn't know what it's saying. And yet, it writes your homework. It passes your exams. It writes code that people get paid for. So the real question isn't whether AI is smart or not. The real question is, do we actually understand how this thing works? Because anything you don't understand eventually controls your future. Before we talk about how large language models work, we need to clear up one very dangerous misunderstanding. Most people think AI is some kind of digital brain, a machine that thinks, reasons, and understands the world. That idea is wrong. Large language models are not artificial humans. They don't have thoughts. They don't have beliefs. And they don't have awareness. What they have is math. Let's break down the term large language model. Large, because these models are trained on massive amounts of data. Books, websites, articles, code repositories, trillions of words. Language, because text is the only world they live in. They don't see reality. They don't hear sound. They only see symbols. And model, because this is not intelligence itself. It's a mathematical approximation of how language behaves. At the deepest level, an LLM has exactly one job: predict the next word. When you hear a sentence like, "The capital of France is," your brain instantly answers Paris. Not because you calculated probabilities, but because you understand what France is. An LLM does not understand France. It does not know what Paris is, too. Instead, it has seen millions of sentences where France is followed by Paris. So, mathematically, Paris has the highest probability. That's it. No comprehension, no meaning, just statistics. So, why does it feel intelligent? Because language itself is a record of human thinking. When you learn the patterns of language well enough, you can imitate thinking without actually thinking. This leads to a crucial insight. Large language models don't store facts. They store relationships between words. They don't know what is true. They know what sounds true. And once you understand this, everything else about LLMs starts to make sense. Up to now, large language models, or LLMs, probably sound almost magical. They talk like experts. They can explain complex topics like a patient teacher. They answer every question you throw at them with unwavering confidence. And that's exactly the problem. The biggest illusion we need to break is that LLMs actually understand what they're saying. They don't. They are masters of language, not reality. They don't truly know facts. What they know are patterns. They are incredibly sophisticated at predicting the next most probable word in a sentence. Based on the trillions of words they've been trained on, this fundamental misunderstanding of their nature leads to a phenomenon called hallucinations. This is when the model generates information that sounds completely correct, completely plausible, but is utterly false. It's not because the AI is trying to lie to you. It's because the model has no concept of truth or falsehood. It's just following a linguistic pattern that leads to a dead end. Another major illusion is objectivity or neutrality. We like to think of computers as unbiased, but LLMs are a mirror reflecting the data they were trained on. And that data is the internet all of it. If the training data contains biases, stereotypes, or prejudices, the model will inevitably learn and reproduce them. There is no perfectly clean, neutral version of the internet to train on. So, an LLM can't be perfectly neutral either. What about reasoning? LLMs can certainly simulate the process of reasoning. They can follow steps, construct arguments, and solve certain kinds of problems. but they don't reason the way a human does. With flexible, abstract thought, they're just following learned patterns of logic they've seen in their data. When you present them with a novel problem that falls outside those familiar patterns, their logic often breaks down in strange and unexpected ways. And here's the most dangerous part. They are supremely confident, even when they are completely and utterly wrong. That unearned confidence can easily mislead people, especially when the stakes are high. Imagine taking advice from a confidently wrong AI in fields like medicine, law, or finance. The consequences could be disastrous. It's also crucial to remember that LLMs have no memory of your past interactions unless they are specifically designed with a memory feature. They have no self-awareness, no consciousness, no intentions, and no goals of their own. Each interaction is, in a way, a fresh start with a machine that knows nothing about you or itself. So, if you remember one thing from this, let it be this. Large language models are incredibly powerful tools, but they are terrible authorities. Use them to assist your thinking, to generate ideas, to summarize text, but never, ever let them replace your own critical judgment. Thanks for watching, and don't forget to subscribe for more insights into the world of airports up to this point. We've turned text into numbers, tokens, vectors, pure math, but numbers alone don't create intelligence. Something has to process them. At the core of every modern AI system is something called a neural network. A neural network is not a brain. It's inspired by the brain, but it's much, much simpler. It's a massive network of numbers connected by weights. Weight decides how important one signal is compared to another. When people say an AI learns, this is what they mean. The system adjusts billions of tiny weights, so its predictions become slightly better. No memories. No understanding. Just optimization. Earlier neural networks had a big problem. They processed text one word at a time. They forgot long-term context. Long sentences broke them, meaning was lost. In 2017, everything changed. A new architecture was introduced. The transformer. The transformer is powerful for one reason: attention. Attention allows the model to look at all words in a sentence at the same time and decide which ones matter most. Look at this sentence. The trophy dose and tea fit in the suitcase because it is too small. What is too small? What is too small? The trophy or the suitcase? You know the answer instantly. That's attention. Third, the transformer builds relationships between every single token. Every word asks every other word. How important are you to me? That's why LLMs don't lose context easily. This process doesn't happen once. It happens across dozens, sometimes hundreds of layers. Each layer refines meaning a little more, from grammar to logic to style. This is why LLMs feel like they understand. They don't. They are just extremely good at modeling relationships between words. And once these relationships are calculated, the model is ready to make a prediction. At this point, you might think, if these large language models are so powerful, why not just release them to the public directly? That's a great question, but the answer is a little scary. Raw, pre-trained language models are dangerous. They are essentially a mirror, reflecting the internet exactly as it is, warts and all. And that brings us to the internet problem. The internet contains the sum of human knowledge, which is incredible. It has brilliant ideas, life-saving information, and beautiful art. But it also has bad information, conspiracy theories, hate speech, deep-seated biases, and some very dangerous instructions. A raw LLM, one that has only been pre-trained, has no way of telling the difference between good and bad. It just sees patterns in data. It doesn't know what's helpful and what's harmful. It just knows what's statistically likely. So, after this initial pre-training, models go through a crucial process called fine-tuning. This is where we start teaching them how to behave. Real humans create high-quality examples to show the model what good behavior looks like. They demonstrate how to be helpful, how to answer questions politely, and most importantly, how to recognize and refuse harmful requests. This step is like sending the model to a finishing school. It's where it starts to develop a useful and safe personality. But the most important and talked about step is called RLHF, which stands for Reinforcement Learning from Human Feedback. Imagine a video game where you get points for good moves. It's a bit like that. Real human reviewers are shown different answers from the model and they rank them. They'll say, this one is good, this one is okay, and this one is really bad. The model then uses this feedback to learn which types of responses get a reward, a high score, and which ones get penalized. It constantly adjusts its strategy to maximize its reward, just like a gamer trying to get a high score. Now, here's a very important detail to understand. The model is not actually learning morality or ethics. It doesn't suddenly develop a conscience or understand right from wrong in a human sense. It is learning reward patterns. It figures out that certain types of answers are consistently ranked higher by humans. The model doesn't care about being good. It cares about getting the highest possible score from its human trainers. It's a subtle but critical distinction. This entire process of fine-tuning an RLHF is what we call alignment. It's the massive, ongoing effort to align a machine's complex behavior with human values and expectations. The goal is to make these incredibly powerful tools helpful and safe for everyone to use. It's not a perfect system, and there's a lot of debate about the best way to do it. But it is absolutely necessary for the responsible development of AI. And this brings us to a fundamental trade-off. Alignment makes models safer and more useful, but it also makes them more constrained. A perfectly aligned model might be more helpful, but it could also be less honest at times, avoiding controversial topics or giving sanitized answers instead of just the raw facts it learned from the internet. This tension between capability, safety, and honesty is one of the central challenges defining modern AI. So far, large language models, or LLMs, probably sound pretty magical, right? They can talk like seasoned experts, explain complex topics like the best teachers, and answer just about any question with a ton of confidence. And that, right there, is exactly the problem. The single biggest illusion about these models is that they actually understand what they're saying. They don't. Not at all. LLMs are designed to model language, not reality itself. They don't truly know facts. What they know are the statistical patterns in the massive amounts of texts they were trained on. They are masters of mimicry, not masters of knowledge. This fundamental limitation leads to a very strange and risky phenomenon called hallucinations, too. This is when the model generates information that sounds completely correct, plausible, and well-structured ... but is utterly false. It's not because the AI is intentionally lying to you. It's because it has absolutely no concept of truth or falsehood. Its only goal is to predict the next most likely word in a sequence based on the patterns it has learned. If a fabricated fact fits the pattern, it will generate it. Another huge illusion is that these models are somehow objective or neutral. They aren't. LLMs are a direct reflection of the biases present in their training data. Think about it. The internet, books, articles, all of it was written by humans, with all our inherent biases. If the data used to train the model is skewed by historical injustices, stereotypes, or unbalanced perspectives, the model will inevitably absorb and reproduce those biases. There is no such thing as a perfectly clean, neutral dataset from the internet. And what about reasoning? LLMs can definitely simulate the process of reasoning. They can follow logical steps and produce arguments that seem sound. But they don't reason the way a human does, by applying abstract principles and understanding context. Instead, they are following learned patterns of logic they've seen in their training data. When a problem requires a novel approach or falls outside of these familiar patterns, their logic completely breaks down, often in very subtle and unpredictable ways. Now, what's the most dangerous part of all this? It's their confidence. LLMs are often incredibly confident even when they are completely and utterly wrong. That unwavering, authoritative tone can easily mislead people, especially when the stakes are high. Relying on a confidently wrong AI for advice in critical fields like medicine, law, or finance. The consequences could be disastrous. It's also crucial to remember that these models have no memory of past conversations unless they are specifically designed to retain it. For a short session, too. They have no self-awareness, no consciousness, no intentions, and no goals of their own. Each interaction is a fresh calculation. So, if you remember just one thing from this, let it be this. LLMs are incredibly powerful tools that can assist our thinking. But they are terrible, terrible authorities. 2. Use them as a creative partner or a research assistant, but never, ever let them replace your own critical judgment. Thanks for watching. Sonali, we know what an LLM really is. A system that predicts the next word. But that raises a much bigger question. Where do those predictions come from? Large language models are trained on data at a scale the human brain can't even imagine. Not thousands of documents. Not millions. Trillions of words. This data comes from everywhere. Books, websites, news articles, forums, documentation, a holiday, and massive amounts of computer code. Basically, written human knowledge. But here's an important detail most people miss. The model does not browse the internet while answering you. It doesn't look things up. Everything it knows is frozen at training time. So, when an LLM answers you, it's not recalling a document. It's reconstructing language patterns based on the vast dataset it was trained on. Now, comes the most important mental shift you need to make to truly understand this technology. Large language models don't see words the way you and I do. They see tokens. A token is a chunk of text. It might be a whole word, part of a word, or sometimes just a symbol or punctuation. For example, take the word unbelievable. The model might see it as 3 separate tokens, unbelieve and able. And here's the key. Each of these tokens becomes a number. For an LLM, your sentence is not text. It's a long sequence of numbers. Every question you ask, every prompt you write, is converted into math before the model even starts thinking. This is why your prompts matter so much. Small changes in your wording can create completely different token patterns. And different patterns lead the model down different predictive paths, giving you a different answer. This is also why LLMs can handle multiple languages, computer code, and even emojis. To the model, everything is just tokens. English, Python, or math equations. It's all the same type of numerical data. There. And once your text becomes tokens, it's finally ready to enter the machine's real engine. If you're finding this helpful, hit that subscribe button, because what comes next is the magic behind it all. Up until now, the model has processed your text, understood the relationships between all those words, and built a massive, complex mathematical representation of what it all means. It's done the heavy lifting of comprehension. But now comes the final, crucial step. It's decision time. 1. A large language model generates text. It doesn't choose words in the way you or I might tick. It calculates probabilities. And it does this for every single possible next word in its enormous vocabulary. Imagine a giant cosmic lottery where every word has a ticket, and some tickets are much more likely to be drawn than others. The model is essentially looking at the text it has so far and asking, given everything I've seen, what's the most statistically likely word to come next? For every word that could follow, there's a score, a probability. Let's use a simple example to make this concrete. Imagine you type the phrase, "I love programming in." Nestled inside the model, in a fraction of a second, thousands of potential next words light up. Python might get a very high probability score. JavaScript would likely be close behind. C++ and Java would also have strong scores. But a word like clouds would have a probability close to 0. The model knows, based on trillions of examples from the internet, that people who love programming usually talk about programming languages, not weather patterns, after that specific phrase. Now, here's where it gets interesting. The model doesn't always pick the word with the absolute highest probability. If it did, every answer would be incredibly predictable and boring. Sometimes, it samples from the top few options. It might roll the dice, giving a slight chance to the second or third most likely word. This controlled randomness is exactly why AI responses can feel creative, spontaneous, or even a little bit unpredictable. It's not just spitting out the most obvious answer. It's exploring the space of plausible language. But make no mistake, it is never truly random. It's always guided by those underlying probabilities. And this leads to something really important to understand. A high probability score does not mean something is true. It only means the sentence structure sounds correct and statistically common. It means the sequence of words is plausible based on the training data. This is the core reason why an AI can state something completely wrong with absolute, unwavering confidence. The sentence, "The sky is made of green cheese," might be grammatically perfect and sound plausible if the AI was trained on a weird set of children's books. The model isn't checking facts. It's just completing a pattern. Now, hold on, because here's the most mind-bending part of the entire process. The model doesn't generate whole sentences or paragraphs at once. It generates text one single word at a time. After it picks a word, say Python, that new word is immediately added to the input. The entire context has now changed. Still, the model runs the whole probability calculation all over again to decide the next word. What comes after? I love programming in Python. Maybe it's because. And once because is chosen, the process repeats. This creates an infinite loop, a continuous cycle of prediction. Each new word that's generated becomes part of the prompt for the very next word. This loop of predict and repredict continues. One word after another, building the response piece by piece until it reaches a conclusion or a designated stop point. So, this is the truth of it. A large language model doesn't really write sentences. It survives, moment to moment, by predicting the next word,